You've heard the word blockchain 100 times by now, but here's the question almost nobody stops to actually answer. What is it, technically? What's actually happening inside? Not the marketing version, not the buzzword version. The real mechanical engineering answer, explained so clearly that after this video, you could draw it on a whiteboard and explain it to anyone. That's what this topic is. Let's get into it. Let's start at the smallest unit, the block. Think of a block like a page in a notebook. Every page holds a certain amount of written information. Once that page is full, you move to the next one. And just like a notebook, the pages are ordered, page 1, page 2, page 3, in a sequence that tells a story. A block in a blockchain contains 3 core things. Number 1, data. This is the actual content being recorded. In Bitcoin's case, it's transaction records, who sent how much to whom. In other blockchains, it could be smart contract code, medical records, supply chain events, whatever the network is built for. Number 2, a hash. Think of a hash as a fingerprint. Every block has its own unique fingerprint, a fixed length string of characters generated by running the block's data through a mathematical function. Change even one character inside the block, one digit in a transaction amount, and the entire fingerprint changes completely. This is what makes tampering detectable. Number 3, the previous block's hash. This is the connection. Every block stores the fingerprint of the block that came before it. That's what creates the chain in blockchain. Block 1 has its own hash, block 2 stores block 1's hash, block 3 stores block 2's hash, and so on, forever. Now here's where it gets powerful. Let's say someone wants to go back and change a transaction in block 47. The moment they change anything in block 47, its hash changes, its fingerprint is now different, but block 48 was storing block 47's old fingerprint. Now they don't match. Block 48 is invalidated, so the attacker has to fix block 48. But fixing block 48 changes its hash, which breaks block 49. They fix block 49, which breaks block 50. They'd have to recalculate every single block from block 47 all the way to the present, and do it faster than the rest of the entire network is adding new blocks. On a large blockchain like Bitcoin, with thousands of nodes running simultaneously, that is computationally impossible. This is why blockchain data is called immutable. Not because it's physically locked away, but because the mathematics of changing it without detection is practically unsolvable. So now you understand why it's called a blockchain. It's not a poetic name, it's a literal description. Blocks, containing data and fingerprints, chained together cryptographically, each one referencing the one before it, going all the way back to the very first block ever created. That first block has a special name, the Genesis block. It has no previous hash because there was no block before it. Bitcoin's Genesis block was created by Satoshi Nakamoto on January 3rd, 2009. It's still there. Unchanged, permanent, the foundation of everything built on top of it. Now, let's zoom out from the block and look at where the blockchain actually lives. In a traditional system, a bank, a hospital, a government database, data is stored in one central place, one server, one company in control. If that server goes down, the data is unavailable. If the company is corrupt, the data can be manipulated. If a hacker breaks in, all the data is at risk. Blockchain works completely differently. Instead of one central copy, the entire blockchain, every block, every transaction, all the way back to the Genesis block, is copied across thousands of computers around the world simultaneously. This is called a distributed ledger. Every participant who runs the software holds an identical copy of the entire history. There is no headquarters, no single server, no company in the middle. If one node goes down, the network doesn't even notice. The other thousands of copies are still running. If someone corrupts one copy, it's immediately obvious because it doesn't match the other thousands. The ledger is everywhere, and because it's everywhere, it can't be controlled by anyone. The computers that hold these copies and keep the network running are called nodes. Think of nodes like citizens of a country. Each one holds a copy of the law, the blockchain, and they all constantly cross-check each other to make sure no one is trying to rewrite the rules. There are different types of nodes depending on the blockchain, but the two most important are full nodes. These store the complete copy of the blockchain from the very first block to the latest one. They independently verify every single transaction and block. They are the backbone of the network's security. Light nodes, these store only a small part of the blockchain, just enough to verify their own transactions. Mobile wallets typically use light nodes because storing the full chain on a phone isn't practical. Every time a new block is added to the chain, all full nodes update their copy simultaneously. The network reaches agreement, called consensus, and the new block becomes a permanent part of the record. We'll go deep on consensus mechanisms in a dedicated topic. It's one of the most fascinating parts of blockchain engineering. The architecture that connects all these nodes together is called a peer-to-peer network, or P2P. In a traditional client-server model, you have one powerful server and many clients depending on it. YouTube's servers go down. Millions of people can't watch videos. Your bank's system crashes. You can't access your money. In a peer-to-peer network, there is no central server. Every node is both a client and a server simultaneously. Every node talks directly to other nodes. This is the same architecture that made BitTorrent so resilient. There was no single server to shut down. Blockchain uses the same principle, but instead of sharing files, nodes are sharing and validating a financial and data ledger. The result is a network with no single point of failure, no one to call to take it down, no one server to hack and corrupt everything. Let's put the full picture together now. When someone initiates a transaction on a blockchain, let's say you send cryptocurrency to a friend. Step 1, your transaction is broadcast to the entire P2P network of nodes. Step 2, nodes collect multiple pending transactions and group them together into a candidate block. Step 3, the network runs its consensus mechanism, a process where nodes agree that these transactions are valid and legitimate. Step 4, once consensus is reached, the new block is given its unique hash, the previous block's hash is recorded inside it, and it is added to the chain. Step 5, every node in the network updates their copy of the blockchain instantly. Your transaction is now permanent, immutable, verifiable by anyone, controlled by no one. Let's bring it home. A blockchain is not magic. It's not a buzzword. It is a very specific, very elegant piece of engineering. Blocks holding data, connected by cryptographic fingerprints, copies of those blocks stored on thousands of nodes around the world. A peer-to-peer network with no center, no single authority, and no single point of failure. The result is something the world has never had before. A system that allows strangers to agree on truth without trusting each other and without trusting a middleman. That's the architecture. That's the foundation everything else in this course is built on. In the next topic, we go one level deeper into the cryptography that powers all of it. Hashing algorithms, public and private keys, digital signatures, and how your wallet actually works. See you in topic 5.